Up to now, we've been talking about springs, horizontal springs and vertical springs, but now we want to talk about a different oscillating system, and that's going to be the pendulum. So if you think about a ball that is on a string and pulled back a little distance and let go, it's obviously going to swing back and forth. So that looks like oscillations. So the question is then, is it simple harmonic motion? Can we model it with simple harmonic motion? How does the math and the physics compare to what we've been doing up till now? So this is the geometry of what's going on, but then we need to think about the forces involved. So the forces are now more complicated. We have a tension force and we have a gravitational force, and the orientation between those two is going to depend on theta. So the best coordinate system to use here is actually something thinking about circular motion, a radial direction and then a tangential direction. So the radial direction, all of our tension is in that direction, and it is balancing the gravitational force in the radial direction. Remember that tension is one of those forces that you can only find from an equation. You don't just know a priori what it's equal to. And we see that our object is changing where it is in the tangential direction, but if we think about our pendulum, it isn't actually accelerating in the radial direction, which is why the tension would be equal in any given point to the radial component of gravity. That leaves a tangential component of gravity. So what happens then? The tangential component of gravity is going to be the net force in the tangential direction. And again, I've skipped the step of going through what's going on in the radial direction, but the answer is it's not accelerating there, so there you have, in that component, you have equilibrium. So the net force would be m, and then your acceleration in the tangential direction, and mg is our total component magnitude of gravity, and then sine theta, where this is the angle with respect to the vertical, tells us how much is in the tangential direction. So you can think of that, there's the vector up here on the tangential line, but it's also that one. This is our FG in the tangential direction. So we now have how our acceleration relates to our tangential force. And remember that we can then relate acceleration to our second derivative, but we have to think about what component we mean here. And before, on the previous slide, I talked about s being the arc length. That's actually what we want to think about here. It would be weird to call the position in this direction t, since t usually means time. So we don't want to call position in the tangential direction time. S is the arc length, and that actually would trace out kind of part of the circle. So that's what we're talking about when we're talking about s. And still acceleration, so second derivative. So we then equate that back, noticing that mass is going to cancel on both this side and that side. So we're left with minus g sine theta. So we have to stop at this point, because up till now we've talked about in simple harmonic motion, you have an acceleration that's equal to negative some constant times the position itself. And that's the idea of a linear restoring force, that the force we have bringing it back to equilibrium needs to be proportional to how far it is from equilibrium. And that's not actually what we have here. We have arc length on the left and we have angle on the right. So this is a problem. We can't actually solve this with simple harmonic motion. And if you want to sit down and actually come up with a differential equation, say what's the answer to this, I mean this in itself is differential equations, this in itself is a really hard problem to solve. So we need to play a little bit of mathematical games in order to get this back into a form that relates to simple harmonic motion. So again, when we think about differential equations, one of the ways that I told you you could solve differential equations is by recognizing that you know what the answer is. And what's important to recognize here is that you don't know the answer to this one. And if you were to look it up in a textbook, you would realize, oh, this is going to be really hard and complicated. So let's use a different approach, which is to try to manipulate this until it is in a form that we can work with.